In a pristine lab, a neural network is pure mathematics, but a factory floor is chaotic and loud, governed by extreme heat, friction, and vibration. When state-of-the-art machine learning models are moved out of that clean software environment and dropped directly onto a manufacturing line, they almost always fail. Software code executes within deterministic virtual limits. Factories, however, are strictly constrained by the unforgiving laws of physical engineering. This friction introduces a critical industrial requirement known as RAMs: reliability, availability, maintainability, and safety. In a software environment, an algorithmic failure is a bug. On an assembly line, that same failure can result in a high-speed mechanical collision, destroying millions of dollars in equipment. Reaching the level of Industry 5.0 requires more than simple software integration. We have to re-engineer the algorithmic foundations themselves to survive in a physical environment. This chart maps AI's evolution in manufacturing. The 1960s established flexible, automated machining. The 2010s introduced IoT connectivity for Industry 4.0, enabling isolated neural network pilots between 2014 and 2021. But a deployment gap separates these from integrated systems expected by 2035. The next-generation ecosystem requires generative AI, large-scale foundation models, and autonomous agents capable of operating across complex workflows. Crossing this barrier marks the shift from Industry 4.0's focus on digital efficiency to Industry 5.0's focus on human-centric resilience and physical adaptability. This diagram illustrates the architecture of a smart manufacturing system, conceptualized as a tree. The advanced branches, like autonomous manufacturing, require highly specialized machine learning techniques acting as the roots to support them. Standard deep neural networks are purely data-driven. They recognize statistical patterns with high accuracy, but they possess zero innate understanding of physical laws. For example, an AI might analyze historical data and determine that increasing machine speed by 20% yields the highest theoretical output. But because the model doesn't understand the thermodynamics of friction, it doesn't realize that doing so will overheat and seize the spindle. If that model commands a milling tool to execute an impossible trajectory, the tool will instantly shatter against the steel block. To solve this, we must implement the first necessary root of industrial AI, physics-informed machine learning, or PIML. PIML injects strict physical principles, like fluid dynamics or thermodynamics, directly into the neural network's architecture as an inductive bias. This bias ensures the algorithm's search for a solution is restricted to the realm of physical possibility, leaving a defined safe zone to explore. Industrial AI must be engineered to obey the laws of physics before it can be trusted to optimize a production line. In safety-critical sectors like aerospace, operational reliability must be absolute. A single unexpected failure carries massive financial and safety consequences. Advanced deep learning is often a black box. The mathematical decision-making layers are so opaque that even the engineers who design the model cannot easily reverse engineer why it reached a specific conclusion. This becomes an issue when an autonomous CNC machine receives a sudden emergency stop command from the AI, halting production. If the operators cannot interrogate the model to see exactly why it triggered the stop, they cannot safely restart the system. They are left in a state of operational paralysis. This trust deficit is why explainable AI, or XAI, is a mandatory route for industrial systems. XAI forces the algorithm to generate an interpretable map of its logic alongside its final command. It traces the stop decision backward, pointing directly to the specific sensor anomaly that triggered the alert. In industrial engineering, an optimized decision is functionally useless if human operators cannot verify its logic. Scaling AI across an entire enterprise requires addressing a final barrier: the severe inconsistency and noise of data scattered across different legacy factory systems. This often leads to failures in domain adaptation. A model flawlessly trained on one specific machine will often fail when deployed on an identical machine in the next bay. These failures occur due to microscopic distribution shifts, tiny variations in sensor calibration, vibration, or ambient noise that make the data look foreign to the algorithm. Federated learning is the architectural route designed to solve these distributed data silos. Instead of pooling sensitive, proprietary factory data into a central cloud, individual machines train the model locally. They extract only mathematical weight updates to send to the central hub, leaving the raw data locked at the local level. This decentralized approach allows industrial AI to learn from the entire enterprise network while adapting to the local physical anomalies of each machine. Once the foundational roots of physics, trust, and scalability are established, we can integrate them into a unified system architecture. This diagram outlines the convergence of the physical and virtual worlds, the fundamental architecture of the industrial metaverse. The physical space contains the human operators, the machine behaviors, and the legacy hardware, like PLCs and SCADA systems that run the shop floor. In the cyberspace, the central AI hub acts as the connective tissue, linking physical telemetry to the digital twin. This creates a continuous, bidirectional feedback loop. Raw sensor data updates the model, while predictive commands and cognitive adaptations flow back out to control the physical hardware. In this mature architecture, the digital twin functions as an autonomous agent, exerting direct control over the physical system based on its internal predictive intelligence. Because this system is capable of autonomous action, there is a common misconception that industrial AI is designed to remove humans from the factory entirely. The actual goal is human-to-X collaboration. This architecture is designed to augment human engineering, allowing operators to safely guide massive robotic systems with perfect precision. Emerging technologies like industrial large language models and semantic frameworks will soon act as intelligent co-pilots on the shop floor. These co-pilots translate massive arrays of machine data into natural language, allowing a human operator to interrogate the system and make rapid, informed decisions. Building the future of smart manufacturing requires us to look past the hype of generic AI. It requires treating machine learning as a deeply integrated, physics-bound, and human-centric engineering discipline.